TI ESD team. My name is Eric Newman. I'm an electrical engineer. My involvement in the project involves testing and calibration of the device. Amir Kiana, he's our team lead, also electrical engineer. He was involved with circuit design and PCB design. Ruchi Shaw, also electrical engineer. She was involved with the soldering and documentation of our project. And finally, John Coxwell, involved with the automation. Our project involves the testing of electrostatic discharge failure in semiconductor devices for TI, specifically the human body model. Our approach to this problem was to build a pulse current source device that we call the TI pulse. The basic idea for the design came from an LED driver made by Professor Paul Smith at the University of Cardiff. And what we did first was take this block diagram, and what that did was show us how each stage interfaces with the next stage. From that step, we went on to our circuit diagram. From there, we took the components and implemented on a test board, or excuse me, a breadboard for testing. After many modifications, we went from there and finally put on a PCB. Now, a few key points on the PCB include it's a modular design, so it allows for future expansion, compactability. It fits in a nice, small, little portable box. The PCB also eliminates the parasitic effect of the wires that we saw during the breadboard phases. The ideal current pulse we're looking for is right here. It's a pulse width of 100 nanoseconds and an amplitude of 0.1 to 2 amps. You can see our final result here is contained in this little box right here. We have two output options for our device. The first one is a lower voltage option. This allows testing for transistors up to 24 volts. And then we have the after transformer option here on the bottom, and that allows testing up to 60 volts. The difference between those is the option for the transformer allows us a higher current. So if you take a look at this example right here, we're testing an 11 volt transistor. And for the transformer, our device allows us 300 milliamps current. And after the transformer, it allows us only 105. That's due to the effects of the transformer dividing the current by a factor of 3. A couple modifications we made after the design was to automate everything using our Arduino interface controlled by Lackey. This allows us automation of a few options, including the pulse width and the amplitude. A few of the features of the device include the free run option or externally triggered option. Free run means the device can trigger itself and create a pulse by itself, or we can hook up an external triggering device into our TI pulse and have that trigger a current pulse. The device is completely portable. It's powered by a 9-volt battery, but we can also plug it into a wall as an option, which is usually our preferred option. And finally, we have a sync output to our device. Now, this can be used to trigger an oscilloscope or other devices, and it aids in timing across multiple devices. We'll be demonstrating our device and its full functionality afterwards at the poster session, and we invite you to come out and see us. Any questions? Yes, sir.
How well regulated was the current when you got to like 100 nanoseconds? Those small pulses?
It was actually pretty good. It's a very, very stable pulse, especially for that small of a pulse width, and it stays pretty stable throughout the whole entire range of operation, especially before the transformer. Now here we introduce the transformer effects. So some of these pulses you can see aren't nearly as clean as these.
Did you vary the load so that you could?
Yes, yeah, these are all different loads right here. So this one is an 11 volt device. This one's a 2 volt device, and over here we have a 23 volt device.
Did you see the impact of the ringing? Does that distort the measuring result?
I'm sorry,
Is it the ringing of the signals you see? There's a substantial overshoot. Does that impact the actual analysis?
Well, what it does, the main thing we're looking for is the energy of the whole entire pulse. So meant by varying the pulse width, we can change that energy as well. So we have many options to change the energy. That's what we're looking for, is the energy of the electrostatic discharge. Yes, sir.
On the PCB, I can't really see the schematic. Is the Arduino chip on the PCB, or is the Arduino? Because I didn't see the Arduino platform.
It's not on the PCB. You can see our device later